Hello, my name is Mackenzie Maxwell, and this is my magnetic field of a bar magnet lab. The purpose of this lab is to measure the distance dependence of the magnetic field due to a small bar magnet and compare the measurements of the distance dependence predicted by the equations for the on and off axis magnetic fields derived from the PHYS law. This was done using GlowScript to create a computational model in order to determine the theoretical magnetic field. And by this, we are going to compare these computational values and the experimental values in order to determine the relationship between distance and the magnitude of the magnetic field. The results are as follows. As the distance from the magnet increases, the magnetic field decreases. The magnetic field of a point on the parallel axis as the magnet is twice as strong as those on the perpendicular axis, and the experimental and the computational models differ in their values. The n found in this experiment was negative 2.6758, and k derived from a equation that we'll see later is equal to 8.382 to the negative 7, 10 to the negative 7. The mu is also 3.8837. The fundamental concepts and assumptions for this lab are as follows. The modeling magnetic field versus distance formula is the topmost level. We also have the on-axis B field formula and the PHYS law. The initial conditions include the system and surroundings, the system being the phone and the magnetometer, and the observation location is at this magnetometer, and the surroundings being the bar magnet and the Earth. The primary B field source is the bar magnet, but the other is the Earth, so both must be accounted for in our calculations. The modeling formula will also be used in the slides next. For this experiment, the first four photos on the leftmost part are the setup, and we're going to record the value of the y component of the Earth's magnetic field and the approximate location of the spreadsheet. We're going to mark on axis the tape of the phone being used for measurements to record data, which is this bottom one with the red. And then we're going to use the same experimental setup used for this, which is going to be these four pictures, and where b net is equal to 100 mu t, and record. We're going to record the value of the y component. We're going to move this into a distance d, and we're going to correct the y component and calculate the magnitude of b net. We're going to also repeat this 2 more times so that we have good measurements. Summary results. The observations are that the x component of the magnetic field increases as the magnetometer moves closer to the bar magnet, and the x component is approximately 0 when the magnetometer is a large distance away from the bar magnet. We can also calculate for mu by looking at the equation that the graph shows us. The n is going to be the negative 2.6758, and we can calculate for k by using the negative 13.992. Here's the GlowScript for this lab for the computational model. We solve for dipole B by calculating the R mag and the R hat and the B. And then we also have our observation of axis 1, our observation locations of the various places with the vector as well, and the distance that is calculated for. We have dperp, which is our value that we calculated previously, and as well as the observation of the 45 degrees. The GlowScript on the rightmost picture shows the calculations of the different axes and the different vectors that will show where the magnetic field originates. To the right, we have the results from the computational model as seen on the GlowScript. We have the b-axis 1, the b-axis 2, the perpendicular axis 1, 2, 3, and 4 as follows. We have the d, which is calculated for us here as well. And we also have the 45-degree distance d, which is from the picture on a few slides prior. The observed results, which are the experimental ones, are as follows, with b net equal to 5.648 10 to the negative 5, and the computational, which is also seen underneath the visual. The possible sources of error include inconsistencies in measuring regarding the magnetometer itself. Other nearby electronics influence the magnetometer's measurements, and excess movement of the phone between measurements and experiments. If the meter stick was at some intermediate angle containing Earth's magnetic field, the results would vary by the x component. With a change in the x component, the n and k values would also differ due to the interference of Earth's magnetic field. Based on the experimental and computational values, the experimental value would differ even more than the computational value if this were the case. If two identical magnets were stuck together end to end, we could expect the magnitude of the resonance to double without changing direction. This logic is possible with the concept of superimposition. In the end, the results would be the same, however, the magnitudes would be different.